Hello and welcome to the Daily Space for Wednesday, August 15 of 2018. I am your host, Dr. Andres Plazas, and as always, we're going to bring you a roundup of today's news from space and astronomy. Dr. Pamela Gay is traveling to the meeting of the International Astronomical Union in Vienna, Austria. So, wishing her safe travels for what should be a very fun meeting. But for today, we're going to talk about three topics. The first one related to the solar wind, the second one related to the first galaxies in the universe, and the third one related to the oldest rocks on Earth. So let's get started. Let's see. There you go. All right. So for the first study that I wanted to talk about today, this is related to how solar wind shockwaves push ions into the interstellar gas at the edge of what we think is the heliosphere, or the edge of beyond the solar system. And this is a study that has been made using measurements from the NASA's New Horizons spacecraft, and it shows that shock waves in the solar wind transfer energy to the ionized interstellar atoms. So as the solar wind flows out from the sun at supersonic speeds, it blows up a bubble which is known as the heliosphere. And this heliosphere encases all the planets in our solar system and even much of the space beyond them, effectively separating the domain of our sun from that of interstellar space. And as the solar wind blows out of the sun, it can exchange energy with the interstellar atoms and molecules. And the researchers from this study have measured this energy exchange using instruments on board the New Horizons spacecraft that, as we know, was launched in 2006 with the primary mission of studying Pluto. So the team have observed how solar wind shock waves that are fast-moving solar wind pulses that could be created, for example, by solar flares. They have observed how these solar wind shock waves give a significant energy boost to ionized interstellar atoms, while the solar wind particles caught up in the wave suffer an energy loss due to this collision. So this is a result that is important because it confirms a decades-old prediction that such a transfer of energy to interstellar ions is the primary mechanism by which solar wind shock waves lose energy as they travel out through the solar system. And this is also a finding that may help researchers understand the origin of the high energy particles that can be found in the solar system through this exchange of energy in these processes. So yeah, that was the first story that I wanted to talk about today. It's a little bit short, but then I also found out two more stories that are a little bit longer and have to do now with cosmology. The first one of them has to do with cosmology. So for the second story of today, we're going to talk about the cosmic web and the first galaxies in the universe. So this is a study made by a team of astronomers from the University of California, the campuses in Riverside, Santa Monica, and Los Angeles. And they have found out that in a surprising way that about 12.5 billion years ago, that is to say about 1 billion years after the Big Bang, the most opaque place in the universe contained actually relatively little matter. So just to give a little bit of context, it has long been known that the universe is filled with a web-like network of dark matter and gas, what we call the cosmic web. And this accounts for most of the matter in the universe, whereas the galaxies like our own Milky Way make up only a small fraction. We have talked about this and we call this the baryons, or the ordinary matter. And In addition, the gas today, the gas between galaxies is almost totally transparent because it is kept ionized. That is to say, the electrons have detached from their atoms. And this is because there is an energetic bath of ultraviolet radiation that is causing this ionization and therefore causing the gas to be what we call transparent. Then, over a decade ago, astronomers have noticed that in the very distant past, as I said, about 12.5 billion years ago, the gas in deep space was not only highly opaque to ultraviolet light, but its transparency varied widely from place to place, obscuring much of the light emitted by these distant galaxies. Then a couple of years ago, one of the teams led by one of the researchers in this current study, they found out that these differences in opacity were so large that either the amount of gas itself or more likely the radiation in which it is immersed must vary substantially from place to place. And this is a little bit weird because today we know we have experimental observation verification that we live in a fairly homogeneous universe on the largest scales of more than 100 million light years, or 100 megaparsecs as we call it in cosmology. And uh, if we so we mean by this that if you look in any direction, you find that on average you're going to find roughly the same number of galaxies and similar properties for the gas between the galaxies, or the so-called intergalactic gas. And but then they had this observation that at an early time the gas in deep space looked very different from one region of the universe to the other. So to figure this out, the researchers used one of the largest telescopes in the world, the Subaru telescope on the summit of Mauna Kea in Hawaii. And this is one of the most powerful cameras in the world, and the team used this powerful camera to look for galaxies in a very large region of about 300 million light years in size, where they knew the intergalactic gas was extremely opaque. So they had two hypotheses of what they could observe. So they said that first, if the region had an unusually small number of galaxies, then the scientists would be able to conclude that the starlight could not penetrate as far as expected through the intergalactic gas. On the other hand, if it had an unusually large number of galaxies, the implication would be that the region had cooled significantly over the previous several hundred million years or so. So, in other words, having few galaxies in a region would mean not only that there was less light created by those galaxies, but also that even more opaque gas was being formed. So the light could not travel as far as astronomers had expected. So in the end, the researchers found out that the region that they studied contains far fewer galaxies than they expected, and this was interpreted as clear evidence that a starlight could not get through. This lack of galaxies could be the reason this region is so opaque. So one of the researchers points out that it is not that the opacity is a cause of the lack of galaxies, but instead it is the other way around. So they concluded that because the gas in deep space is kept transparent by ultraviolet light from galaxies, as I mentioned before, then the fact that we observe fewer galaxies might means that it actually the gas is murkier. Now, fewer galaxies might make it murkier. This is a research that was published in the Astrophysical Journal, and it has some implications because the researchers point out that in the first billion years after the Big Bang, ultraviolet light from the first galaxies filled the universe and made the gas in the deep space transparent, as I said. This would have occurred early in regions that had more galaxies, right? The astronomers could conclude, due to what we have said in this, that they have found in this study that more opaque regions means the fewer galaxies means more opaque regions. So on the other hand, a universe first filled with galaxies would make it more transparent. So that would be the opposite conclusion. So the astronomers plan to further study whether the void and the voids in the universe or the others like it will reveal clues about how the first generation of galaxies illuminated the universe during that early period. And of course, we hope that studying these galaxies and the gas in deep space will reveal more about how the intergalactic ecosystem took shape during the period in that part of the universe, the early universe. So yeah, that was interesting, I thought. And then I also found another story related to to Earth and rocks and geology, which I usually don't read much about, but I also find very interesting and fascinating. So this is a story in which researchers have found that the Earth's earliest known rocks were probably formed by heat from meteorite bombardment about 4 billion years ago. And this is important because it shows that the early development of the Earth was shaped by a different process than what we find today. And we already knew or had evidence pointing towards the fact that about 600 million years after the formation of the Earth, there was a period of what is called the heavy bombardment period. So this might show evidence for that. So the researchers actually analyzed two types of volcanic rocks. So we're gonna back up a little bit and try to explain what this type of rocks are. So there are two types of rocks, of volcanic rocks. Ones are called mafic rocks, and the other ones are called felsic rocks. So these two words are used most often in the context of igneous rocks, and they inform about the chemical composition of the various types of rocks. So mafic is used for silicate minerals, magmas, and rocks which are relatively high in heavier elements. And this is a term that is derived from using the ma syllable from magnesium and the fic syllable from the Latin word for iron. So it's a made-up word constituting those two parts. And on the other hand, the word felsic means is used for silicate minerals, magmas, and rocks which have a lower percentage of the heavy elements on the opposite side of as mafic, and are correspondingly enriched with lighter elements such as silicon and oxygen, aluminum, and potassium. And this is a term that comes from fel, the syllable fel from feldspar, which in this case is the potassium-rich variety, and sic, which SiC, which indicates the higher percentage of silica. So you can get a little bit more precise, and then in the classification, you can do a scale of classification based on the silica content. And rocks that are therefore divided into ultramafic, mafic, intermediate, and felsic. And just in summary, mafic rocks have about 45 or 55% of silica, whereas felsic rocks have about over 65% of silica, the highest of all types. So coming back to our story, the scientists have found that rocks that are about 4 billion years old, about 500, 600 years after the formation of the Earth, they have found that there are rocks that are rich in silica. So they found these felsic rocks from the Acasta River in Canada, and they found out that probably these rocks form at very high temperatures and at a surprisingly shallow depth of the planet's nascent crust. So the high temperatures needed to melt the shallow crust were likely caused by what we call a meteorite bombardment around half a billion years after the planet formed, as I said, 500 million years. And this melted the iron-rich crust and formed the granites we see today. So felsic rocks are granites. And these results are presented for the first time. They were presented for the first time in a conference that took place yesterday in Boston, and published in the Nature journal, in the Nature Geoscience journal. So again, to give a little bit more of context, as I was saying, about 4 billion years ago, or between 4 and 3.8 billion years ago, there was a period of intense comet and asteroid bombardment, and there are certain lines of evidence in favor of this. Now, many of the numerous craters found on the moon and other bodies in the solar system record this event, and as I have mentioned several times in the past when we have talked about the moon, this is one of the things that we want to do with citizen science projects that you can find on CosmoQuest, such as moon mappers. We can count the number of craters that you find on the surface of the moon, and then you can know more about the history of the moon, and therefore the history of the Earth, and therefore the history of the solar system. So there is one theory that says that there was a gravitational surge caused by the orbital interaction between Jupiter and Saturn that sent this interaction sent Neptune into the ring of comets in the outer solar system, and these disrupted comets were sent into all directions and collided with the planet. So that is one theory of how this period of heavy bombardment came out. So there is a problem, right? So we would like to find the record for this event, and you can, as I said, you can find a record of this event in planets or objects of the solar system that are, so to speak, geologically inert, such as the moon or maybe Mercury. But the Earth is actually still active, and because of this activity and other effects such as erosion, then the track or the evidence for this type of bombardment on the surface gets lost, because the surface gets constantly renewed. So that's part of the reason why the research that we're talking about today is important. So scientists, coming back to our story, from these rocks found in Canada, in the Acasta River, these felsic rocks found in Canada. So scientists have long known that these rocks are from the Acasta River are different to the majority of the felsic rocks that we see today in other places, such as the granites that are widely used as building rocks or even decorative material. So after doing a modeling, different types of modelings, scientists find out that this type of rocks from Canada could have only been formed at low pressures and very high temperatures. And then scientists believe that the primitive crust of the Earth was largely comprised by dark and silica-poor mafic rocks. So there was the question, right, of how these felsic rocks from the Acasta River could have formed. So the modeling showed that this type of felsic rocks derived from they derive from the melting of pre-existing iron-rich basaltic rocks or mafic rocks, which formed in the uppermost layers of the crust of the primitive Earth. And so they use methods to show that these felsic rocks were produced by partial melting of the original mafic rocks at very low pressures, and it would have needed something very special to produce the 900 temperatures that you have to have in order to generate these early felsic rocks at such low pressures but high temperature. And this is interpreted as evidence in favor of the existence of a drastic event, most likely what happened that was caused by the meteorite bombardment. So yeah, so this is the last story that I wanted to share with you today, and I hope that you found it interesting, and let's see what you all have to say. with respect to the stories of today. I'm gonna look at the chat and read out your comments, look at your questions. And well, let's start by saying hi to everyone. To Radio Geek, to Paranor, to Tom Fan Scooter, UHE Cosmic Rays, hello Guido V, hello Perpitown, hello Honey, Admiral Vic Mech, hello Astro YYZ. Um, yes, I think Pamela took the intro with her on tour. Yeah, I don't know why we didn't have the intro today. Yesterday we didn't have the camera, and then Pamela showed me that it was something very trivial. So probably the lack of intro today is also something very trivial, and I'll try to figure it out for tomorrow. Hello Scott. Hello Tecker Kev. Yes, the camera is working perfectly today. Turned out that that Dr. Pamela had to change cameras, and then we only needed to press a button to inform the software that that was the case. But if you don't know which button to press, then that's what I didn't know. But hopefully yesterday you didn't miss my face too much. We have my face today here. I'm just still saying hi to everybody. Larry. Honey asks, does the magnetic field of the sun envelop the solar system? Does that also protect us from cosmic rays? I'm not quite sure about that. Let's see. I'm not so sure about the fact that the magnetic field of the sun actually extends that far. So we do have these shock waves produced by the solar wind that as a consequence of the solar flares. So they made it up to that part of the outer solar system. I don't know exactly about how they would maybe also provide a protection from other particles out of the solar system. We do, from the story of today, we do see that of course there is an interaction between the solar wind, that are these ionized particles, and the particles that are coming from outside of that boundary. So in a way, this sort of interaction could mean a type of protection. However, if you have very energetic particles coming from outside of the solar system, then maybe the interaction is not as effective with the solar wind, and then you don't find this type of protection. So there is actually a prof that is called IBEX, IBEX, that is actually trying to measure the particles that bounce back from the interaction of the solar wind and what you find beyond that in the interstellar medium. So as I was saying, you find this interaction and some of these particles keep going, but then some of the particles actually are able to bounce back due to the interaction at this boundary, and then you can measure the type of particles that you get back and the energy distribution of those particles. But I'm not sure about the type of energy distribution that they might have. So that's something that I would like to check. I don't think it extends that far. I do think that what extends that far is the solar wind, and that's what I believe is happening. Larry says the STD is interstellar, not intergalactic. Yes, I think it's interstellar. Maybe I said intergalactic. It's interstellar. Sorry for that. Paranor actually looked up the Wikipedia article, thank you very much, about the interplanetary magnetic field. There you go, thank you very much. Could they use the distribution of opacity of the early universe to definitely tell whether black holes form from or before galaxies? Well, they could use that opacity in order to tell us about the distribution of galaxies themselves. And by extension, you could tell that if some of those galaxies are harboring a type of black hole or not, depending on the type of black hole of type of black hole that we're talking about, right? As we said in the past, we have said in the past, there are different types of black holes in terms of their masses, and the ones that you find at the center of a galaxy, such as our own Milky Way, are supermassive black holes that have more than million solar masses. And by knowing the inventory of the amount of galaxies that you find in the early universe, then you can also, by extension, try to figure out what fraction of those galaxies can harbor these type of black holes. About other type of black holes, then I'm not so sure about that. But yeah, that's what I would think. Um, could they learn from So Hani is asking us, could they learn more about Earth crust from studying the moon, or is it too mixed up from formation? Um, I believe they do. They are able to find out information about the Earth, because one of the theories of the formation of the Earth tells us that it actually the moon. I'm sorry, the formation of the moon tells us that it formed from debris that came from an impact, something that heavily impacted the Earth, and then you have all these debris that formed around the Earth, and that eventually led to the formation of the moon. So more the details about that, like what is the extent to which they can learn about the composition of the Earth. I'm pretty sure there is a limit, and as you mentioned, then you find all this mix of the formation, and depending on the nature of the primordial impact that created this debris to begin with. So I would say that yes, you can learn about the composition of the Earth, of the crust, but I'm not so sure about like the details of what would be the limit of what you can find from that information. Twitch being twitchy with icons again. Perpitan says, good to have your face back with us. Thank you. It depends on the energy of the cosmic rays. When did the moon form versus the bombardments? What is the timeline? So the bombardments, they happened between about 4 billion and 3.8 billion years ago. And the moon that happened before, about um, the same time when the Earth was formed. I think I don't know exactly. So the numbers, of course, that I have in my head is that the Earth formed about 4.6 billion years ago, 4.5 billion years ago, and the Earth formed about the same time. I'm being a little bit vague here, but it definitely happened before the period of the heavy bombardment, and it's one of the reasons why we find all these craters on the moon and places like Mercury as well. Yes, I think Astro YYZ gave us that answer, the same answer. So thank you. um, all right. So, do you guys have any more comments and any more questions? So now that I have joined the Astronomical Society of the Pacific and the CosmoQuest team as a research scientist, I have been working closely with another scientist from our organization, Matt Richardson. So Dr. Matt, he's been doing most of the work on this, but he's been using the counts from the craters of the moon that the public have input into our website, into CosmoQuest, and we're trying to turn that into a research paper, and we're working on that. And it's been a fascinating topic for me, coming from cosmology now, learning more about this period of bombardment and how you can know more about the history of the solar system and the moon just by counting the craters, and then you can create a distribution of the number of craters according to their size, and there are models that tells you how old then the craters are depending on how many mm, craters you count for each particular size. So I think that this is a fascinating topic, and every day I'm learning more along with Dr. Richardson. So yeah, uh, yeah, just to letting you guys know. So hopefully, yes, in the future we will have a publication, a research publication out of this, and hopefully we'll be talking about that here with you, because this is thanks to all your help. All right. Okay, I just wanted to give that comment related to the last story of the day, but I think maybe we can call it for today. And as usual, thank you so much for watching. And this has been the Daily Space, a production of CosmoQuest, created by the Astronomical Society of the Pacific. If you like this show, please give us a follow, and if you want to sustain our efforts, please consider subscribing. And the Daily Space will be back tomorrow and every weekday at 1 p.m. Eastern, 10 a.m. Pacific, and 6 p.m. London. And I believe that after this next up on this channel, we will have Dr. Matthew Richardson, if I'm not mistaken. So please stay tuned. And I'll see you guys tomorrow. All right. Bye bye.